Okay, PCAP BC, Unit 3, Day 5, lesson. So we're going to kind of continue with our optimization ideas, but apply them to some more kind of business type problems with revenue and profit and costs and things like that. And that's kind of a new twist on what we were doing, last year. So we didn't really do anything exactly like this. So give a little background on it. Now, when it really comes down to it, I mean, I'm going to show you guys a couple kind of interesting results, but really these problems are they're just EVT problems. They're just optimization problems. They're just extreme value theorem problems. So you can just pretty much use what we've been using on other problems. It's just a new kind of set of applications. So profit is revenue minus cost. Okay, so we're going to be using that idea. And so here's sort of a generic revenue curve and cost curve. Doesn't necessarily mean it's realistic or whatever, but I'm just going to use it as a simple example to show a couple things. So you have cost and you have revenue. So one question that we might ask ourselves is we want to know, where do we find the max and minimum profits? And those are both kind of extreme cases of where things that we might be looking for. Now, I'm going to tell you right now, I'm just going to give you up front, maximum profit occurs when the slopes of these cost and revenue curves are equal to each other. So it'd be interesting to try and figure out, well, why does that make sense? So like you might notice right here and here, they're kind of like parallel to each other, and like here and here, they're parallel to each other. So those in general are corresponding. They got to be at the same point, I guess. Those are corresponding to a special case, a good one or a bad one. Now, the area under the cost curve will give you the total cost, and the area underneath the revenue curve is going to give you the total area. So at this point, cost is more than revenue, and this is the place where it is the worst. This is your maximum loss because you have more cost than revenue. But here, the revenue is the greatest distance away from the revenue. The revenue is the greatest distance away from the cost curve. This represents your maximum profit. So let's figure out why. Okay. Now the slopes of these, we actually have some kind of special names of them. But the slope of the revenue curve we call the marginal revenue. And maybe this is these are terms that maybe you've seen in maybe an econ class. So marginal revenue, or just I'll call it MR for short for our notes. It's the revenue from one additional item. Okay. And so it's the slope of the revenue curve. And so the curve is changing, but at this point, this is how the revenue is changing with respect to the next item being made. So, and then the slope of the cost curve is going to be called the marginal cost. So similar idea. Okay. And so right here, this shaded region, this is all profits. This shaded region, this is all territory where we're making a profit, I guess a positive profit. So marginal cost, MC, as the cost of one additional item. It's the slope of the cost curve. And then profit would be the profit of one additional item. And that's gonna come, that would be the slope of the profit curve, which we don't have, but profit equals revenue minus cost. So we could take the derivative of it to get the marginal profit. So this is the marginal profit. Now, the interesting cases are going to happen where this marginal profit changes from positive to negative or negative to positive. It's going to be when it equals 0. And this is, this is essentially a critical point. This is a relative max or min. So this is kind of an interesting case right here that when the marginal profit equals 0, you're getting relative maxes, mins. I guess you could also consider the endpoints. Now, the max and the min profit are going to happen when this is equal to 0. So that's going to, if we solve this, it's going to be where the marginal revenue equals the marginal cost. Marginal revenue equals marginal cost. Now, this result that relative maxes mins happen when the derivative equals 0 is not a crazy idea to us. This is what we've been using for a long time. Okay, so this is kind of another interesting result of this. Now, like I said earlier, we could just use EVT, and that's really the approach I'm going to take. I don't really want to memorize new things if I can just use the same technique. So here's an example. We're going to do a few examples. T-shirts, they sell for $2 each. That's the price per shirt. Okay, and then this is the cost of the of all of the shirts when you produce X. This is total cost when X shirts are made. Okay, so the profit is going to be the revenue, which is going to be, it's always $12 a shirt times how many shirts, X. That's your revenue, right? And then we're going to subtract the cost from it. Now, this cost expression has multiple terms, so I'm going to put parentheses around it first to make sure I don't forget to distribute. Okay. So, we could write a new profit function. It's going to be 6x minus 500 minus 0.2 x to the 3/2. And let's find the derivative, the marginal profit. So it's going to be 6. This is going to be minus 0.3 x to the 1/2. And we're going to set it equal to 0 undefined. And so then we get 0.3 x to the 1/2 equals 6. And divide both sides by 0.3. And we get x to the 1/2 equals, now 6 divided by 3 is 2, but this is going to be 20. And then you're going to square both sides. Don't take the square root. That is a square root. We're going to square both sides, no plus or minus, and we get 400. So this is our critical point. Now, we're going to try and justify these. I mean, we could just assume this is relative to max profits or min profits, but that's kind of a dangerous thing to do. So we're going to support it. Now, I'd say there's like no endpoints. I mean, there's kind of an endpoint. Like, you're not going to make negative shirts, but what is the upper endpoint? I get you can make is however many shirts. You can't say, oh, well, when you lose money, you're not going to make shirts. No, that's not true. A lot of times you lose money early on. So there's no endpoint. So we can't do EVT. I mean, we could try and kind of do a table, but maybe we'll try a first derivative test. FDT instead. And so we do a line check with P prime, put the critical point on it. I mean, we could say 0 is definitely an endpoint. Test a point, x equals 0. Why not? If you plug in the derivative, it's positive, negative. So it's increasing, decreasing. So this critical point is a relative max. But because it's the only one, and that is definitely the highest point, it's going to be absolute max. So, you could also do second derivative test if you want, but that's just extra work. So I think that, this is going to be our max. Now, our max profits, we still got to figure out what the max profits are. They happen when we make 400 shirts, but we still got to plug these in. Uh, 0.2 is 2/10 is 1/5. 400 to the 3/2 would be 1/2, and then cube it. So this is going to be 2,400 minus 500. This is going to be 20. Cubed is going to be 8,000, I think. 8,000 divided by 5. So I think that's going to end up being 5 goes into 120 times, 200 times into 1,000. So I think that's going to be 1,600. So 1,900 minus 1,600 equals 300 for our profits. So we could say the maximum profits are $300 when selling 400 t-shirts. Now, the way to justify this is you'd say, well, since P prime of X is positive on the interval 0 to 400, and P prime is negative on the interval 400 to positive infinity. So I'm doing first derivative test justification here. Therefore, there is a relative maximum at x equals 400 by the first derivative test for relative extrema. Now we gotta justify, well, why is the relative max an absolute max? So then you would say, since this is the only, relative extrema, it is an absolute maximum. So this would be kind of sort of the justification if you're not going to use EVT. If you're going to do FDT, I've been kind of avoiding this, but this is more, you're going to justify first that it's a relative maximum, then you got to justify why it's special and it's an absolute maximum. Yep. A couple more examples in the back, or yes, one more. And here's another interesting thing. But again, in the end, we're not going to necessarily need to remember this because you could always just use your calculus knowledge. But cost, so we've been talking about marginal cost and marginal revenue. So what about average cost? That'd be so there's a total cost to make 100 items, but the first 25 might cost more or less than the next 25. So maybe we want just the average cost. And that would be the simple idea of just the total cost divided by the number of items. So that's not a crazy idea. And then we could say, well, let's minimize the average cost. So we'd need to take the derivative of our average cost. And if we do, I'm doing this very generically, I don't actually have an expression. So we could do, quotient rule low, D high minus high, D low, all over low squared, set it equal to 0 undefined. And 0 would have to be the top. Undefined is this. That's x equals 0, which is a pretty boring place. If you don't make anything, that is potentially a minimum average cost of 0. But you're not really doing any business. So I'm going to set the top of this equal to 0 because we think this is probably where the more interesting conclusions are going to come. And so then C prime of x equals C of x over x. Now this is interesting because this is the marginal cost, and then this is the average cost pops back up. So when the marginal cost equals the average cost, you're going to get minimum, or you're going to get relative minimum, relative max or min average cost. Again, you don't need to remember that because you could, I'll show you. So this next problem, here's the cost. For what x is the average cost minimized? Okay, well, we could find average cost, which is total cost divided by x. And this time, since we have an expression, we don't have to get so, generic about it. And we actually get x squared minus 6x plus 15. We get a function. So we're like, well, average cost minimized, we just want to do EBT on this, or fundamental thermodynamics. So we do AC prime, which is 2x minus 6. We're going to set it equal to 0 and define. And we're going to solve. 2x equals 6, x equals 3. So this is a critical point. X equals 0. Technically, is a place where this happens, but that's boring. We're assuming we're going to actually make something and not just create a business that doesn't end up doing anything. So, then we could, try and justify it. Maybe first derivative test to kind of help us. Test x equals, now I guess we put 0 in there. It's maybe positive, negative, increasing, decreasing. So clearly a relative min by the first derivative test. And so now you'd have to put that all into writing. And by the way, the average cost you don't really know yet. So you plug 3 into the average cost, you get 9 minus 18 plus 15, you get 6. So the minimum, that's a maximum. Did I make a mistake? This might be the maximum average cost. Maximum average cost. The minimum, I guess, would have to be, I don't know. Maximum average cost is $6 per unit when producing 3 units. So something like that. Now, to justify it, you'd have to say, since there is a relative maximum at 3 units by the first derivative test, for relative extrema. It's not enough to name it. You got to tell us how it works. So you would say, well, AC prime is positive on the interval 0 to 3, and AC prime is negative on the interval 3 to positive infinity. So therefore, that's why it's a relative maximum. And then you'd have to say, well, it's the only absolute max. So It's the only relative. So, there you go. I guess, yeah, it looks like a. Just make sure I didn't make any mistakes anywhere. It's the average cost. 2x squared minus, ooh, no. Yeah, I don't know. I'm not sure where else. So if we plug 0 into that, it's good. Oh, I was plugging the wrong thing. I plugged 0 in here, so it's actually negative, positive. So I thought that was weird. It's like, why would I make the problem? So this is decreasing and this is increasing. This is relative min. So this is relative min. So I made a little mistake there. I tested it in the wrong thing. So relative minimum. First derivative test, it's actually negative first, and then it's positive. So sorry for the mess. All right.